In 1963, archaeologists digging inside a limestone cave on the southern coast of Italy found two skeletons locked together in an embrace. One was an adult. One was a teenager. They had been buried that way deliberately, wrapped around each other, 12,000 years ago, and left undisturbed until the moment someone's trowel finally reached them. For more than 60 years, this burial was treated as a beautiful mystery nobody could fully solve. Both individuals were unusually short. The younger one had strikingly shortened limbs, dramatic enough that early researchers assumed they were looking at a young boy with some kind of skeletal abnormality, the specifics of which stayed permanently out of reach. You can measure a bone. You cannot read a diagnosis off it, not with the tools archaeologists had in 1963, and not for decades afterward either. In January of 2026, that finally changed. And the answer that emerged wasn't just an interesting footnote about ancient bones. It was a genetic diagnosis. The kind a doctor today would write on a chart. Applied successfully to a person who has been dead for 12,000 years. The cave is called Grotta del Romito on the southern coast of Italy. The two individuals inside are known simply as Romito I and Romito II. Romito II, the younger of the pair, stood about 110 centimeters tall, roughly 3 feet 7 inches, with limbs noticeably shortened relative to the rest of the body. Romito I, the older individual cradling them in burial, stood about 145 centimeters, several inches shorter than the average adult height estimated for people living in that era. For 60 years, all anyone really had to go on was, these two people were short, and one of them was strikingly so. Bones alone couldn't say why. An international research team led by Daniel Fernandez and Ron Pinhasi at the University of Vienna, working alongside Adrian Daly at the Liege University Hospital Center, decided to revisit the burial using tools that simply didn't exist in 1963. Modern ancient DNA sequencing combined with clinical genetics. The same kind of genetic analysis a hospital might use today to diagnose a rare disease in a living patient. What they found rewrites the story almost completely. First, the genetic analysis revealed something the original archaeologists never could have guessed from bones alone. Romito I and Romito II were closely related, almost certainly mother and daughter. And second, buried in their DNA was a clear genetic answer to the question that had lingered for 60 years. Romito II carried two altered copies of a gene called NPR2, a gene essential for normal bone growth throughout the body. Carrying two altered copies, what geneticists call a homozygous variant, produces a specific, well-documented condition, acromesomelic dysplasia, Moreau-Taux type. It's a rare inherited skeletal disorder defined by severe shortening of the limbs and significantly reduced stature, exactly matching what researchers could already see in Romito II's actual bones. For the first time, an ancient skeleton had received something that functions, in every meaningful sense, as a real clinical diagnosis. And then the second half of the discovery landed, the part that turns this from an interesting genetic finding into something almost unbearably human. Romito I, the mother, cradling her child in that grave for 12,000 years, carried only one altered copy of the same gene, a heterozygous variant. In modern clinical genetics, this pattern is instantly recognizable. It's exactly what you'd expect from a parent who is a carrier of the same recessive condition expressed fully in their child. The mother wasn't randomly buried beside her daughter. She passed this gene to her, biologically, the same way a parent might today, without any way of knowing what a gene even was. Researcher Adrian Daly summarized the significance of the finding simply. Rare genetic diseases are not a modern phenomenon. They have been present throughout human history. It sounds almost obvious once stated, but it had genuinely never been proven this directly before, this far back, in an anatomically modern human. This single case forces you to rethink something most people assume without ever questioning it. The idea that conditions like dwarfism, or any rare inherited disorder, are somehow a byproduct of modern life, modern chemicals, or modern genetics gone wrong. They aren't. The exact same mutation, in the exact same gene, producing the exact same condition doctors diagnose in hospitals today, was already quietly present in human populations at the literal end of the last ice age, 12,000 years before anyone had a word for chromosomes, genes, or DNA. But there's a second layer to this discovery that may matter even more than the diagnosis itself, and it has nothing to do with genetics directly. It has to do with what daily survival would have required. A young person with a chromosomelic dysplasia, living in a hunter-gatherer community at the tail end of the Ice Age, would have faced real physical limitations. Reduced mobility, difficulty traveling the distances required for hunting and foraging, likely difficulty competing physically for food in a world with no agriculture, no permanent shelter beyond caves, and very little margin for error. And yet the skeletal evidence shows Romito, too, survived not just into childhood, but into the teenage years. Evidence of sustained growth and care over a long period of time, in an environment that offered absolutely no safety net for anyone who couldn't keep up. Researcher Alfredo Coppa, who led the study from Sapienza University of Rome, put it directly, her survival would have required sustained support from her group, including help with food and mobility, in a genuinely challenging environment. This wasn't a person hunting and foraging independently. This was a person who, by every reasonable expectation of that era, should have struggled enormously to survive at all, and instead lived long enough to grow into adolescence, fed and protected, almost certainly, by people who had every reason to leave her behind and chose not to. This single grave is increasingly being read by archaeologists as part of a much larger pattern researchers have started noticing across the prehistoric record, that caregiving, particularly within families, particularly toward those who couldn't fully provide for themselves, wasn't a rare exception in early human societies. It may have been a consistent, deliberate survival strategy practiced even in small, resource-scarce communities where every single calorie theoretically mattered. So when you picture that cave again, two skeletons wrapped in an embrace, sealed in limestone for 12,000 years, waiting for someone with the right tools to finally understand what they were looking at. You're not just looking at a medical curiosity confirmed by modern genetics. You're looking at proof, written directly into bone and DNA, that long before written history, before agriculture, before anyone could have explained why. Human beings were already choosing to keep the most vulnerable among them alive. The gene didn't survive 12,000 years on its own. It survived because somebody decided it was worth the effort to make sure it did.